We last time we learned the LSTM, and also I explained about how transformer works. Okay, so and the most important part is this one. I mean, the most important part was this page. So, I mean, the first thing you have to notice is this figure is same as this figure. Okay, so both are containing the encoder and decoder architecture. And in this figure, the left side is the encoder and the right side is the decoder. Okay, and you have to notice that because the transformer it processes the inputs in the parallel way, so it cannot encode any positional information. So you have to actually add some of the position information, which is called as positional encoding. Okay. Okay. So and the output of the encoder is the feature vector that encodes the input sequence. And in the decoder, its aim is to output some new sequence using the encoded feature and also the input to the decoder. Okay, so their combination is actually happened in this attention mechanism, which is called as the cross attention. So the decoder input, they are first applied with the masked attention, okay, and then it is applied with the cross attention to combine it with the encoder feature, and then the final output is generated. Okay. So today I may explain a bit more about the attention mechanism, and I will explain how this transformer architecture could be used in the vision domain. Okay. So as I told you, this is the input to the transformer, and I already told you that the same vector, same input, this is denoted as the addition of the positional encoding with the word embedding of the student. Okay, so this is the new input actually added with the positional encoding, and actually this is kind of a one-dimensional vector. Okay, and we will transform it to three kind of new vector, which will be called as the query key value. We will denote it as QKV. Okay. This is actually transformed from the original input using this kind of linear operation. So this W is the weight vector you have already learned. When given this X input, we multiply W and add bias B. Okay, you can regard this W same as this operation. So this is multiplying some weight to the one-dimensional vector. Okay, and actually, anyways, this is the parameter of the transformer. Anyways, you transform the original input vector to the key query value. This is the new intermediate feature. And the attention mechanism is, summarized here. Okay, so as I told you, when describing this attention mechanism, I told it like this. So as I told you that we will densely dot product the two inputs, okay, when calculating the attention. Okay, so that is actually happening here. So the query of I is multiplied with key of all other input. Okay, so they are actually dot producted. Okay, so student their feature is multiplied with weight k, and then the k feature is generated. Okay, and I mean you can do the same thing for other input. So for I, you can calculate 3 vector. I mean, so Qi, Ki, Vi. Okay, here you will get these 3 vector. Okay, by multiplying the same weight to the this input. Okay, you can get this kind of key query value for each word. Okay, and then the thing you will do is you will densely product key and queries. Okay, so and you will get one-dimensional, I mean, scalar value. Okay, depending on their similarity. Okay, I'm not sure. I mean, this dot product is somehow measuring the similarity of these two vector. So by dot producting these two vector, anyways, this kind of scalar value is obtained, and we can interpret that as the similarity between two vector. Okay, and then we multiply the value vector we obtained. Okay, and by adding them, the final attention value is obtained. Okay, so this is kind of how to calculate, I mean, the attention mechanism. Okay, how to apply maybe attention mechanism. Okay, it looks like this. So we can somehow, if we write it in the formula, it looks like this. So we product the key and queries for all input, and we rescale it. And if we apply the softmax, then we can get somehow the weight between each word. Okay, maybe it reflects the similarity between two words, and then we add the original value vector again, and by summing them, we can get the feature for each word. Okay, so I mean, you can also interpret it in this way. So when calculating the feature for this I word I, this is the feature for word I. Okay, when calculating this feature for word I, by producting with all other input, you will first measure the similarity, okay, between all other input and myself, the word I, and then multiply the value feature, and by adding them. Okay, so this value is somehow calculate the contribution from the other feature. Okay, so this is the other words feature, and when combining them to calculate the feature for the word I, you can interpret that you will multiply some scalar value that decides the contribution of that word when calculating the word's feature. Okay, so you can interpret that in that way. Okay, so when deciding the features for one input, you will first calculate contribution for all other input, and then weight summing all other words feature using that contributed weight. Okay, so that's the attention mechanism. Okay, are you guys following this? So this is denoting the case for only one word, but if you extend it, this is kind of the calculation method for multiple words. Okay, so this is the feature for I, and this is the feature for M. This is feature for A. This is feature for student. So this is, I mean, this formula is showing the method for parallelizing this process. But I mean, this part might be easier to understand their inherent meaning, maybe. And also, you can if we product the Q matrix with the a query matrix with the key matrix, then you can get this kind of similarity matrix. So this cell is encoding the similarity between word I and word I. And this is encoding the similarity between I and N, right? So, I mean, yeah, that is actually same as this kind of value obtained for this word I, but by producting this Q and K matrix containing all other input, okay, you can parallelize this process and getting these two-dimensional matrix at once, okay? And this matrix is encoding the similarity between one input to the other input, actually same as this part, okay? And by scaling this, by dividing, actually this is denoting the same matrix, okay, here. And by dividing it by some scalar value and applying softmax, you can make it to have probability, meaning, okay? This is kind of non-bounded, having non-bounded scales, but by applying softmax, you can make it into probability. And by applying by producting with the value feature, you can get this kind of feature for input. Okay, this is the attention mechanism. And actually, the thing you have to note is this is a parameter you have to learn. Okay. So when learning the transformer, when training the deep architecture, using the gradient descent, we have to update the parameter sector, okay, right? And in the CNN, this parameter sector was the filter coefficients, okay? But here in transformer, of course, because we are having the feed-forward network, and this is same as the MLP, multi-layer perceptron, as we learned. I mean, this is also having some parameter, W and B, okay? But when you are asked with questions like, what is the learnable parameters in the attention mechanism, then that answer is this one. So we are actually learning this transformation weight, WQ, WK, and WV. Okay, this is the only parameter which will be learned during the training. I mean, in this mechanism, you will learn those transformation metrics. Okay, that is the parameter sector. Okay. And also, you will notice that this kind of operation, the attention mechanism, is again differentiable. Okay, that is composed of the multiplication, division, and the softmax. Okay, so because of that, this layer, these operations are differentiable with respect to their parameter and respect to their input. Okay, so we can embed that in our deep architecture. Okay? Using the laws, we can apply the gradient descent to update the parameters. Okay? And you also have to notice that nowadays we are not merely using the attention, but we are using multi-head attention mechanism. Okay, this is very simple. Okay, so we have multiple attention. Multiple attention operation. Okay, using the how to say the same input, but having different this weight parameter. We are having actually, if we have a H head, we are having that number of key query value transformation weight, okay, for each head. So by applying the first weight, we can get the first head output, and by applying WHQ, WHK, WHV, we can get H's head attention. And then we can concatenate that and multiply another weight, which is the output weight. Okay. Okay, so that is actually visualized here. So this is original attention mechanism, which is just one head. You will multiply key query and scale it. Sometimes we are applying some masking, but normally we don't. And we apply softmax and multiply with the value matrix. That is the self-attention mechanism I already told you. It is describing this kind of operation. Okay, this is the self-attention mechanism. And this is the extension of the self-attention towards the multi-head attention mechanism. So actually you are having now H number of head. And also your, how to say, the transformation matrix also have multiple weight, okay? And you will apply the single head attention multiple times, H times, and concatenate their output and multiply with some another linear weight to get the final output. That's the multi-head attention. Okay. So by applying this multi-head attention, of course, you can get, improved accuracy. So because of the accuracy, we are using this. But of course, we can maybe reduce the time efficiency, maybe, okay? We may take more, time complexity for doing this, but we can get better accuracy by applying this, okay? So this is the multi-head attention. Actually, this is explaining the same thing. Yeah, so I will skip this part, okay? And also, I will more detail, will explain the masked attention again. So as I told you, in this part, in the decoder side, encoder is one time calculated. They are parallelized, okay? The similarity between inputs are one time calculated and they are added, okay, to get this feature vector for, as the encoder output, they output this feature vector. But decoder works in the sequential way. So at the first round, it only have the starting token, and it output this first output only. And at the second round, it now feed this first round output as the input, and then output the second output, okay? And then in the third round, it input the second round's output and get the third round's output, and it iterated until this end token is obtained. Okay, this is how the transformer is working. And but I mean, this kind of sequential operation is hard to be used during the training stage. I mean, because due to their inefficiency. So actually, when implementing the training, we are actually applying this kind of masked attention. Okay, we can interpret the sequential operation of the decoder, as I told here, as the this kind of attention mechanism. Okay, so I mean, at the first time, if we apply the masking here, okay, I mean, in normal, in the normal key query multiplication, if this is the self-attention, as in here, we will use whole entries of this similarity matrix, okay? But because we have to apply it in the sequential way, okay? Their actual processing is different from the attention mechanism in the encoder. And actually the problematic entries are these ones. So actually when only the starting token is available, then only this starting token is available as the other counterparted output, okay? And when these two inputs are given, when this JE is given, we also, I mean, these two inputs are given as the other token, okay? And also, if we are having this SUIS word, okay, the third output, then we can calculate it with this kind of three word, okay? But this, the last word is still not available, okay, when calculating with this word, okay? So, I mean, because of this sequential operation of the decoder, some entries of this, attention score matrix are not available. So we are assigning minus infinity values to these entries. When after calculating this matrix, we assign minus infinity to these entries and apply softmax to obtain actually the zero value for these entries. Okay, I mean, when applying softmax by applying entries as minus infinity, then the obtained values for that softmax max applied value would be zero. So we are doing that. Okay. The thing, I mean, anyways, we want to make the entries here as zero. Okay. We want to delete that. Because of this, this is called as the masked attention. Okay. Are you guys following this? 다 이해가 되나요? Okay. And cross attention, as I told you, the self attention, the key query values are coming from the same input signal in the encoder, but you can see that the input here are coming from the encoder, but input here are coming from the previous decoder layer's output, okay? So, okay, so the query value is coming from the decoder output, the previous decoder's layer, and key end value, they are coming from the encoder feature, okay? That's the cross attention mechanism, okay? but the attention mechanism itself is same as before, but the input are coming from the different source. That is why we are calling that as the cross attention. But previously we say this kind of operation because their inputs are coming from the same source, okay? Coming from the same source, but we apply it with different weight metrics to transform it to key quality values, okay? So because of that, they are called as self-attention, but here we are calling that as cross-attention. Okay, so this is the transformer, okay? And they were actually used for the NLP task. So far, we learned that for the NLP task, okay, their input are the sentence, which is the word sequence, okay? This is the natural language processing, okay, domains signal, right? NLP, okay. But actually, we are learning the computer vision techniques. And from now on, I will explain how we can extend the transformer towards the computer vision tasks, okay? Actually, I will explain about how we can apply it for the object detection task, okay? And actually, I mean, this is already 5 years ago, okay? This paper, ECCB 20, this is the first paper that proposed this DETR architecture that can perform object detection using the transformer. And they show better performance than faster RCNN. We already learned, okay? This was the state of the art at 2020s, okay? Without any post-processing, this DETR performs better than the fast RCNN. Okay, it proves the robustness in object detection task. So I will explain their brief architecture. So, I mean, this is the input, and we are actually using the CNN pre-trained CNN architecture, and this is actually ImageNet pre-trained that AlexNet or not AlexNet. Usually we use the ResNet for this, okay? So ResNet you already learned, and ImageNet is one of the biggest data set in image classification, having 1,000 classes. So we usually use this as the feature extractor that can encode the image feature. So given this image, we apply this ImageNet pre-trained ResNet to extract some feature vector. And also now we apply this kind of positional encoding to encode, to denote the location of the pixels, okay? Instead of the word, instead of this kind of word, okay? That require only this one-dimensional positional encoding. We now need this kind of 2D positional encoding. And actually we add them together. And those added values are actually inputted to the transformers encoder, okay? And then here we can get the feature vector that encodes the, image feature. So we already have the image feature extracted from the CNN. So you can think this kind of encoder as the feature improver. Maybe using the attention mechanism of the transformer, feature extracted from the CNNs are improved. Okay, you can think like that. And then we can apply the transformer decoder to output. These kind of things are feature, intermediate feature, and they are applied with another feed-forward network. and they output two information, the class information and the bounding box information. Okay, but sometimes I mean you can predict. I mean you have to predict it as the background object. Okay, I mean if the bounding box their locations are estimated here, then we have to estimate it as the null object. Okay. So this kind of information is further inferred from this, the head. So this is called as the head. Okay. So this is called the prediction head. But by further applying this prediction head to the decoder output, you can get the class information and bounding boxes. Okay. This is the DETR algorithm, and the trainable part is the feed-forward network, and actually the transformation for this object query, and also the transformation of the encoder. Okay. As far as I know, mostly the CNN is fixed. Okay, they are freezed. But the important thing you have to note is actually this figure and this figure are also same. Okay. Another important thing when applying transformer into the image domain is previously when we apply the transformer in the NLP domain, you are inputting here some of the starting token and some of the intermediate result from the decoder, previous decoder round. Okay, you have to use the decoder input at that way. Okay, but because in our application, these decoder inputs are no more having some sequential, information. So because of that, we will use this decoder one time. Okay, our how to say decoder input is no more having the sequential information, and because of that, we are also applying normal self-attention in the decoder side instead of the masked attention. We will apply the self-attention for this part. Okay. No more our decoder is working in sequential way. Okay. Or decoder inputs are available from the start. Okay. And they are self-attended to generate all output of the decoder at once. Okay, that is how this DETR is working, and that is actually the difference between the DETR, the object detection transformer, and the previous NLP transformer. Okay, actually this is easier. Because we are applying this transformer in the image domain, this part actually becomes easier. Okay. And this cross attention part is also same as before. Okay. So this is the encoder feature, and we are applying value and key from the encoder output and the queries from the previous layer in decoder. Okay. And we cross-attended it, and at the end, we infer two information, the class probability and bounding box using the prediction head. Okay. This is the head. Okay, so this is rough explanation about the DETR. Okay. So, and this is, you can now know that this is the same figure as this one, right? Okay. And the input to the encoder is now image feature, okay? And also the spatial, 2D spatial positional encoding is used here, okay, to edit with the 2D image feature. And they are self-attended to get the encoder output, and they are cross-attended here. And this decoder input is, to say, inputted to the first self-attention mechanism, and they are further used to, for the subsequent cross-attention mechanism, and they are finally mapped to the class probability and bounding boxes. And also, this is also the same figure for decoder part only. Okay, so this part you can magnify and can interpret it like this. But the most confusing part in this detail is I didn't tell you how these object queries are made. These object queries are becoming some, some one-dimensional vector, but they are, I missed this part, sorry. Actually, I mentioned that this FFN and also the the weight Q, weight K, weight V for this attention, okay, those are learned, okay. And another part we have to learn is these object queries, okay. So these object queries are first randomly initialized, okay. At the first time, it randomly initialized. They are only having some meaningful dimension, okay, to fit to this calculation. Their dimension have to be same as the feature vector coming from the encoder, and the only requirement they have to have is their dimension, query dimension, have to be same as the encoder feature, but their values are actually randomly initialized. And the thing we have to do is we actually update these randomly initialized object queries to maximize their training accuracy. Okay, so these object queries are updated during training. Okay, this is same as some other parameter sector. Okay, so samely as other parameter sector, these vectors are also updated during training to maximize our training accuracy. But after training, when you see these object queries, it has some it is some one-dimensional vector, but it no more have any semantic meaning. In NLP, these queries, these inputs to the decoder is having some meaning. Okay, so this was the input to the decoder. Okay, it works in the auto-regressive way. So the starting token and the intermediate outputs are input to the decoder. Okay. So, but in the image domain, when you apply the transformer in the image domain, you no more have this kind of intermediate output from the decoder, because our transformer will not work in sequential way anymore. So we don't have to make this, this kind of input to the decoder when we apply the transformer in the image domain. So instead of doing that, we first randomly initialize the decoder input, and we anyways update it during the training to maximize our accuracy. Okay. And at the testing, we anyways fix those updated one-dimensional vectors as the input to the decoder. Okay, but it doesn't have much meaning, but it is anyways the trained parameters. Okay, so we will use that during the inference time. Okay, so the strange part is how to set these object queries. That is actually confusing part in DTR. That in original DTR proposed in this ECCB 20, it works like that. It was some random vector and updated during training, and it has no semantic meaning. Okay, but this DTR is also updated every year. For example, there are many variants in DTR, so deformable DTR or conditional DTR, and nowadays there have been DNO. Okay, they are actually improving mostly the object queries to have some semantic meaning. Okay, at first DTR, early DTRs, they don't have any spatial meaning or any semantic meaning in decoders input, but anyways it worked. Okay, but this makes the overall training process takes more time. And it is known that when training DTR, it takes a lot of time compared to the previous CNN alternatives. But by improving these object queries, which is the input to the decoder, people are becoming to know that this training DTR process can be efficient. Okay, so DNO, for example, I forget in which year this was proposed, maybe 24, okay, ICLR maybe. Their inference accuracy is becoming better than DTR, sharing the same DTR, they are same architecture, same transformer-based architecture. They improve the inference speed and at the same time improve the training convergence. Okay, by improving the object queries to give some semantic meaning, and also the other part, the loss functions as well. Okay. Okay, and the other important part when understanding this DTR is you have to understand this bipartite matching part. Okay. As I told you, another important confusing part in DTR is because we are setting this input to the decoders in arbitrary way. Okay, we randomly initialize it and update their weight during the training. We don't know how many object queries we will have. Okay, but we normally set it to 200 to 300, assuming that there would be this number of objects inside an image. Okay, so the number of object queries, they are actually same as the number of our prediction. Okay, so we will get the intermediate feature from the decoder, the same number of encoder feature, decoder output with the decoder input. Okay, and then we will apply the feed forward network for all the decoder output. And then we will get the same number of predictions, okay? So actually the number of our predictions are same as the number of object queries, okay? And we are setting the number of object queries to this number, assuming that in our image, the number of objects will be less than this number, okay? So, and then this, let's say this is the number of predictions, okay? So actually we have 1, 2, 3, 6 predictions. Let's assume we are having 6 predictions, but in the ground truth, let's say we are only have 2 ground truths, okay? Then, and among these 6, let's say some of our prediction is having this kind of prediction, and some are estimating some this kind of bounding box. Okay, let's assume it like this. Okay, in this situation, the thing we have to do at the initial training stage, the thing we have to do is we have to first choose the best matching between ground truth and the prediction. So among these 6 predictions, we will choose the best 2 prediction. We have to choose the best predictions. I mean, how to say, the number of ground truths, number of best prediction we have to choose. Because there are 2 ground truths, we will select 2 top predictions that best matches with our ground truth. Okay, we will then maybe abandon this remaining prediction. And this is the first part. We will select the best matching prediction, best matched prediction, and then apply L2 laws, which is the MSE laws for the prediction, bounding box prediction, and maybe cross entropy laws for the class prediction. Okay, only for this best matched prediction. That's happening in the second stage of the training. Okay, so bipartite matching, that is pointing out the process of choosing this best matching. So, let's say this is our prediction, and this is the ground truth, only having 2 foreground objects, and all others have to denote the background. Okay. So semantic class bird. Okay. Bird. There are 2 birds, and their bounding box location is like this. And the remaining, if there are remaining predictions, they have to denote some background class, and there should be no bounding boxes. That's our ground truth. Okay, but let's say we are predicting something. Okay, and predicting some wrong classes at the early training stage, then we have to match this maybe with this because they are similar. We have to choose this, and we also have to choose this. Okay, to match it to this. Okay, to match it to this, we have to choose these 2 things, and then apply L2 and class laws, the cross entropy laws, to close this more to their corresponding vector, ground truth vector, and to close this more to their corresponding ground truth. Okay, that's the second stage. And first stage, we have to choose these 2 things. Okay, that is called as the bipartite matching. Okay, so actually the training stage composed of 2 parts. Find the optimal prediction set, as I mentioned. Okay, and they are also using the two loss function. So how their bounding boxes, their prediction is matched with the ground truth. They are using this as the loss. And another loss is considering their probability distribution, how they are matched with the ground truth prediction. They are use this as the score and find one best matching, okay, that can minimize this kind of class and bounding box scores, okay. So this is denoting this. So I mean, this sigma is how to say, one sub-element of this large sigma set. Okay, this sigma set is denoting this type of permutation. Okay, so if our predictions are only 6, okay, if we are assuming, let's assume we are estimating 6 output, okay, then the permutation of that six output, maybe there are this number of permutations, okay? That is entire number of elements in this large sigma set, okay? And then anyways, we will choose the best how to say, permutation, okay? So because this element should be matched with the ground truth here, okay? And this element should be matched with this, and all others have to have background object. So that if even though there are predictions, they have to be matched with the background object. Okay. So anyways, in that sense, this is the best matched permutation. So we will choose this. Okay. So that is actually this. So among all permutations of our 6 predictions, based on this probability score and bounding box matching score, we will choose the one best permutation of our prediction. That's the bipartite matching part. And then we actually apply the loss function to close this to this corresponding ground truth and this output to their corresponding ground truth. And that is actually happening in this loss, okay? We apply MSE loss for the bounding boxes, and also we apply cross entropy loss to the class probability, okay? So this is another difference to original transformer because we are having partial meaning, okay? So our output is class probability and bounding box. So we are applying this kind of process, okay? That is also different to the original transform. And this is the result of the DTR, okay? So you can see there was a fast RCNN. This was the state of the art before the transformer-based approach. And AP is the measure for the accuracy. And you can see, of course, the DTR-based method is better than the fast RCNN-based method. Okay. And for the image feature extractor, you can also apply different backbones. And I mean, by changing these backbones, the accuracy is varied, actually. Okay. And also the number of parameters, they are comparable to the CNN-based method, but given this similar number of parameters, the accuracy is better, actually, compared to the CNN-based method. Okay, that's the benefit of the transformer. Okay, so as I told you, I mean, CNN, their convolution operation is actually used in the deep architecture because it is a popular method for processing the images. Okay, at the same time, they are differentiable, but there are no guarantee that those convolution is the optimal operation. Okay, but I mean, indeed, this attention mechanism nowadays they are replacing those convolution operations. Okay. That's the important message from this lecture. Okay, so this is the end of the object detection pipeline, and next time I will add few more things about the training process of the CNN. Okay, and maybe this week we will announce the assignment one. Okay, and also by this weekend we will announce the score for the quiz one, and also we will also publicize the solution for the quiz one. Okay, so. Okay. If you have some claims seeing the scores of your quiz one, then please mail me or please mail to the TAs. Okay. So anyways, that's it, and see you this Wednesday. Okay. Thank you.